Chapter 5 covers the 12-bit analog to digital converter, or ADC12. The LM4F 120H5QR has two of them. Since most microcontroller projects measure and/or control things in the real analog world, the device needs to be able to monitor what's happening out there. One channel of the ADC12 is connected to an internal temperature sensor. You'll use that sensor in the lab to monitor the temperature of the LM4F 120H5QR and experiment with the ADC12. The Stellaris LM4F microcontrollers feature two ADC modules, ADC0 and ADC1, that can be used to convert continuous analog voltages to discrete digital values. Each one of those modules has 12 bits of resolution. Each one can operate independently. You can execute different sample sequences, you can sample any of the shared analog input channels, and you can generate interrupts and triggers with them. The ADC features on the LM4F 120H5QR are two 12-bit 1 megasample per second ADCs with 12 shared analog input channels. Those inputs can be single-ended and differential. There is an on-chip temperature sensor. The maximum sample rate is 1 megasample per second. Due to the low-cost nature of the device and the pin count limitation, there's a fixed reference between the analog voltage and ground. There are 4 programmable sample conversion sequencers per ADC that we'll deal with on the next slide. Separate analog power and ground pins to keep the noise between the digital and analog sides. Flexible trigger control for the microprocessor. The software can trigger it, the timers can trigger it, the analog comparators can trigger it, GPIO can trigger a measurement. We have hardware averaging that we can go between 2 and 64 samples that will be averaged together to generate a result. That's in powers of 2. Each ADC has each ADC has 8 digital comparators. There are 2 total analog comparators for the device. Optionally, you can phase shift and sample time between the ADC modules, and that's programmable from 22.5 to 337.5 degrees. The Stellaris LM4F ADCs collect and sample their data using programmable sequencers. Each sample sequence in the sequencer is a fully programmable series of consecutive samples that allows the ADC to collect data from multiple input sources without having to be reconfigured. Each one of the modules has 4 sample sequencers that control the sampling and data capture. They're all identical except for the number of samples that they can capture and the depth of the FIFO that's associated with it. So in order to configure a sample sequencer, the following information is going to be required for each one of the samples that you want to make. So you configure a sample sequencer with 1 or 4 or 8 different samples, or let's say on one that has 4 samples you might only use 2 or 3. That's all applicable. You configure the input source for each sample. What's the mode? Is it going to be single-ended or differential? Are you going to generate an interrupt on the sample completion? Are you going to indicate that this is the last sample in the sequence? And bear in mind, you could do this for every single sample, right? As many as, for sample sequencer 0, 8 total samples. So each sample sequencer can then transfer its data from the FIFO independently using a dedicated DMA channel. In Lab 5, you'll write code to make measurements with the on-chip 12-bit analog to digital converter. To keep things simple, you'll use the internal temperature sensor as an input to the ADC12. You can then use your finger to warm the microcontroller on the LaunchPad board to see the temperature change. In Lab 5 Step 1, we've already created the Lab 5 project for you with an empty main.c, a startup file, and all necessary project and build options set. Maximize CodeComposer and click Project, Import Existing CCS Eclipse Project. Make the settings shown below in the workbook and click Finish. We're going to import that from our Labs folder, Lab 5 CCS. Make sure that the Copy Projects in the Workspace checkbox is unchecked. What would happen there is it would copy our lab files into the workspace, and then we would actually be doing our project in the workspace. That might change our links to a degree. It will certainly change the fact that the files that we're working on won't be sitting in Lab 5 CCS. They'll be sitting in our workspace. So we actually want to be working out of the lab files here. So click Finish. In Lab Step 2, delete the current contents of main and add the following lines in the main.c to include the header files needed to access all the Stellarisware APIs. The only one you might not recognize there is ADC.h. That's the definitions for using the ADC driver. In Step 3, we're going to add a driver library error routine. The runtime parameter checking by the peripheral driver library is fairly cursory. It's very light, since excessive checking would have a very negative effect on the cycle count. You'd be doing all your time checking instead of actually doing what you're supposed to be doing. But during the debug process, you may find that you've called a driver library API with incorrect parameters, or a library function generates an error for some other reason. The following code here will be called if the driver library encounters such an error. In order for the code to run, debug needs to be added to the predefined symbols for the project. We're going to do that, show you how to do that later. So leave a blank for spacing and add these lines of code after the header entries above. Next up, in Step 4, set up the main routine by adding the 3 lines below. In Step 5, the following definition will create an array that will be used for storing the data read from the ADC FIFO. It has to be large enough, or at least as large as the FIFO, for the sequencer that we're going to use. What we're going to do is we're going to be using sequencer 1. Why are we using sequencer 1? We could have used sequencer 0, but we're going to read 4 of these and then add them together 4 samples off the ADC, and then add them together and divide by 4. So we're going to use sequencer 1, which has a FIFO depth of 4. If another sequencer was used with a smaller or deeper FIFO, then the array size would have to be changed. For instance, sequencer 0 has a depth of 8. So add the following line of code as your first line inside main. So that's setting up an array 4 data points long. In Step 6, we'll need some variables for calculating the temperature from the sensor data. The first variable is for storing the average of the temperature. The remaining variables are used to store the temperature values for Celsius and Fahrenheit. All of them are declared as volatile so that each variable will not be optimized out by the compiler and will be available to the expression or local windows at runtime. Add these lines after the last one. In Step 7, set up the system clock again to run at 40 megahertz. Add a line for spacing, and then add the syscontrol clock set API after the last ones. In Step 8, we're going to use the ADC0 module, so let's enable it. Add a line for spacing, and then add the syscontrol peripheral enable for the ADC0 as the next line. In Lab Step 9, as an example, let's set the ADC sample rate to 250 kilosamples per second. Since we're measuring temperature, a slower speed would be fine, but let's go with this. The syscontrol ADC speed set API can also set the sample rate to additional device-specific speeds like 125 kilosamples per second, 500, or 1 megasample per second. Add the following line directly after the last one. Syscontrol ADC speed set to 250 kilosamples per second. In Step 10, before we configure the ADC sequencer settings, we should disable the ADC sequencer 1. We want to make sure it's off before we configure it. Add this line after the last one, ADC sequence disable, and that's for ADC0 base 1. In step 11, now we can configure the ADC sequencer. We want to use ADC0, sample sequencer 1. We want the processor to trigger the sequence, and we want to use the highest priority. So add a line for spacing and add this line of code. There's the ADC sequence configure, ADC0 base, ADC trigger processor, and so on. In step 12, we need to configure all 4 steps in the ADC sequencer. Configure steps 0 to 2 on sequencer 1 to sample the temperature sensor. That's ADC under CTL under CTS or under TS. In this example, our code will average all 4 samples of temperature sensor data in our code on sequencer 1 to calculate the temperature. So all 4 sequencer steps will measure the temperature sensor. For more information on the ADC sequencers and steps, reference the device-specific datasheet. Add the following 3 lines after the last. So you can see they're pretty much the same, with the only difference being that we're configuring each sequencer step. The final sequencer step, it requires a couple of extra settings. We want to sample the temperature sensor, and we want to configure the interrupt flag, ADC CTL IE, to be set when the sample is done. So we'll tell the ADC logic that this is the last conversion on sequencer 1, ADC CTL end. Add this line directly after the last one. So you can see we're making very much the same thing, configuration choices as before, but we're also turning on the interrupt for this sample, and we're also telling the sequencer that this is the last one. So now in step 14, we can enable the ADC sequencer 1. Add this line directly after the last one. In step 15, still within main, add a while loop to your code. Add a line for spacing and enter these 3 lines of code. That's a while 1 with the open and closing brace. Go ahead and step 16, save your work. As a sanity check, right-click on main.c in the project pane and select Build Selected File. If you're having any issues, check the code in the workbook to make sure that we don't come up with any issues. And that built just fine for us. When you build the code, you may get a warning that UL ADC0 value was declared but never referenced. You can ignore that warning for now. We're going to add the code to use this array later. Inside the while, we're going to read the value of the temperature sensor and then calculate the temperature endlessly. In step 17, the indication that the ADC conversion is complete will be that the ADC interrupt status flag goes off. It's always good programming practice to make sure that the flag is cleared before writing code that depends on it. Add the following line as your first line of code inside the while loop, and that's the ADC int clear, and we're doing that for ADC0. In step 18, once that's done, we can trigger the ADC conversion with software. ADC conversions can also be triggered by many other sources. Add the following line after the last. ADC processor trigger for our ADC. In step 19, then we need to wait for the conversion to complete. Obviously, a better way to do this would be to use an interrupt rather than burn CPU cycles waiting, but that exercise is left for you. Add a line for spacing and add the following 3 lines of code. So all we're going to do is wait for the interrupt status to go off for us. In step 20, when the code execution exits the loop in the previous step, we know that the conversion is complete, and we can read the ADC value from the ADC sample sequencer 1 FIFO. The function we'll be using copies data from the specified sample sequencer FIFO to a buffer in memory. The number of samples available in the hardware FIFO are copied into the buffer, which must be large enough to hold that many samples. This will only return the samples that are presently available, which might not be the entire sample sequence if you were to attempt to access the FIFO before the conversion was complete. In this case, we know it's complete, but it's possible for you to try to access that under some other condition. Add a line for spacing and add the following line after the last. ADC sequence data get, and you can see we're going to grab the entire FIFO. In step 21, we want to calculate the average of the temperature sensor data. We're going to cover floating point operations later, so we're going to make this math fixed point. The addition of 2 here is for rounding, since 2/4 equals 1/2 equals 0.5. 1.5 gets rounded to 2 with the addition of 1/2, and so on. So add this single line. Sorry, it looks a little strange, but it's a single line of code after the last line. You may need to reformat that a little bit in the window. Very nice. So you can see all we're doing is adding together each of the values that we brought in from the FIFO. In step 22, now that we have the averaged reading from the temperature sensor, we can calculate the Celsius value of the temperature. The equation below in the workbook is shown in section 13.3.6 of the LM4F 120 H5QR datasheet. Division is performed last to avoid truncation due to integer math rules. A later lab is going to cover floating point operations. Once this is done, we need to multiply everything by 10 to stay within the precision needed. The divide by 10 at the end is needed to get the right answer. So the voltage ref positive minus voltage ref negative is the VDD on this LM4F 120 device. That means it's 3.3 volts. If you multiply that by 10, because we don't have point in fixed points, and then 75 to get 2475. So enter the following line of code directly after the last. There's your temperature value in Celsius. Once you have the Celsius temperature, calculating the Fahrenheit is a piece of cake. Hold the division until the end to avoid the truncation. Enter the following line of code directly after the last. In step 24, go ahead and save your work and compare it with the code that you see in the workbook. Hopefully it's pretty close. You can find this code, if you're having problems, in main1.txt in your project folder. So back at the beginning, we had the error checking on our APIs, but we have not added a debug predefined symbol. Let's go ahead and see how that's done. In step 25, right-click on Lab 5 in the Project Explorer pane and click Properties. Under Build, ARM Compiler, click the plus next to Advanced Options. Then click on Predefined Symbols. In the top Predefined Name window, add the symbol, all caps, debug, as shown below, and click OK. In future labs, the project will already have this symbol defined for you. In step 26, compile and download your application by clicking the debug button on the menu bar. If you have any issues, correct them, and then click the debug button again. After a successful build, the CCS debug perspective will appear. Click on the Expressions tab. Our windows, there we go. We're having a little bit of a problem with Camtasia here. What we're going to do here is make sure that our values in here are only the ones that we want to look at. So if you right-click on the tab, you can click Remove All. That will get rid of the LED and the pin data values. So now we have no expressions in there. What we'd like to do is find the U1 ADC0 value in our code, right-click on that, or double-click on it to highlight it, and then right-click on it to add it as a a watch expression. So there you go. There you go. We'll do that one. We'll do the UL temp average. The UL temp value C. And temp value F for the Fahrenheit. So we did that for all four of those. In step 28, we'd also like to set up the debugger so it will update the windows each time the code runs. Since there's no line of code after the calculations, what we're going to do is we're going to choose one right before them and we'll display the result of the last calculation. So click on the first line of code in the while loop, in the while one loop. That's ADC int clear. And then right click on it. Select breakpoint, CodeComposer Studio, and then breakpoint to set a breakpoint on the line. Now we're going to change the properties of the breakpoint. Most breakpoints, when you hit them, they just halt. We're going to do something a little different here. Right-click on the breakpoint symbol to the left of the instruction and select Breakpoint Properties. Find the line that contains action and click on the Remain Halted value. You'll see it brings up a pull-down menu. That's the normal way a breakpoint should act, but let's change it to Update View. That's up at the top of the list, usually. There you go. That list seems to reorder itself sometimes. In the dialog that you see, note that only the expressions window will be updated. So you can see that one. Now the variables in the expression window will be updated and the code will continue to execute as we run through the samples. Click the Run button to run your program. Or resume, excuse me. Okay, you'll notice the yellow appearing on the expressions window there. That means that the values are changing. So you'll notice the measured value of U1 temperature average changing up and down slightly. Change values from the previous measurement are always highlighted in yellow. I'm going to use my finger. I'll rub it on my pants leg, and then I'm going to touch it to the LM4F device to warm it a little bit. So you should see the values go up or change a little bit. I also have a cold frozen water here. I'll put my finger on that, and then I'll put it on the device to cool it. So you should see some changes in the values of the temperature. Now bear in mind, the temperature sensor isn't calibrated, so the values displayed aren't exact. That's okay, since in this experiment we're only looking for changes in the measurement. Note how much UL temp average is changing. Not the rate, but the amount. We can reduce the amount by using hardware averaging in the A to D converter. At this point, we're only averaging 4 values. We can do a lot more than that. Click the Terminate button to return to the edit perspective. Find the ADC initialization section of your code as shown below, where you see the syscontrol peripheral enable for the ADC. Right after the syscontrol ADC speed set, add the following line. That's the ADC hardware oversample configure. It says ADC0 base 64. So now you can see instead of 3 lines of configuration code, you have 4. The last parameter in that API function call is the number of samples to be averaged. This number can be 2, 4, 8, 16, 32, or 64. Our selection means that each sample in the ADC FIFO will be the result of 64 measurements averaged together. Since we're going to take that times 4, that means every result that we see in the window here will be the result of 256 measurements of the A to D converter. Build, download, and run the code on your LaunchPad board. you should be able to notice that it's changing at a slower rate by a smaller amount than it was before. In step 32, we're going to take a look at calling APIs from ROM. Before we make any changes here, let's take a look and see how large the code section is for our existing project. Click the Terminate button to return to the CCS Edit perspective. In the Project Explorer window, expand the Debug folder under the Lab 5 project. Double-click on lab5.map. CodeComposer keeps a list of files that have changed since the last build. When you click the Build button, CodeComposer compiles and assembles those files into relocatable object files. You can force CodeComposer to completely rebuild the project by either cleaning the project or selecting Rebuild All. Then in a multi-pass process, the linker creates the output file, that's a .out file, using the memories or the device's memory map as defined in the linker command file. The build process also creates a map file that explains how large the sections of program are, for instance the .text section, which is the code section, and where they were placed in the memory map. In the lab5 map file, find the section allocation map section and look for .text like shown below. So right up at the top, you can see that the length of our .text section is 690. That's in hex. Check yours and write it in the workbook. In step 34, remember that the M4F onboard ROM contains the peripheral driver library. Rather than adding all the library calls that we've done here to our flash memory, we can call them from ROM. This will reduce the code size of our program in flash memory. In order to do so, we need to add support for the ROM to our code. So in main.c, add the following include statement as the last one in your list of includes at the top of your code. You can see that says include driverlib rom.h. So that tells the part we're going to be using the ROM. In step 35, open your properties for Lab 5 by right-clicking on Lab 5 in the Project Explorer pane and clicking Properties. Under Build, ARM Compiler, Advanced Options, click on Predefined Symbols. Add the following symbol to the top window that says Target is Blizzard under RA1. Blizzard is the internal TI product name for the LM4F series. This symbol will give the libraries access to the APIs at ROM. Click OK. And OK. Back in main.c, add ROM, all caps, ROM underscore to the beginning of every driver lib call as shown below. So there's a good first one. Usually what I do is I type the first one ROM underscore, and then I do a copy of that. And then just paste them in, Control V. There you go. Don't forget the one inside the while loop there. And that should be it. That looks good. If you're having issues, this code is saved in your lab folder as main2.txt. Click the debug button to build and download your code to the LM4F 120H5QR flash memory. When the process is complete, click the resume button to run your code. When you're sure everything is working as it was before, click the Terminate button to return to the editing perspective. In step 38, check the section allocation map in lab5.map. Now, our results, let's see, what did we get this time? We got 3E8. The new size for our .text section is 3E8. You may want to compare that in decimal to make sense of it, but that's about 40% smaller than before. That's a significant savings. So what we've done here in step 39, the method here is called direct ROM calls. It's also possible to make what's called mapped ROM calls when you're using devices that may or may not have a ROM, like the TI ARM Cortex M3. Check out section 32.3 in the Peripheral Driver Library User's Guide for more information on that technique. When you're finished, close the Lab 5 project and minimize Code Composer Studio.